Okay, so in this video, we're going to be talking about the DC circuit analysis. Now, the acronym DC means direct current. So basically, this is direct current circuit analysis. Now, the DC circuit analysis involves determining unknown voltages, current, and resistance in a direct current circuit. Now, in analyzing such circuits, Ohm's law is readily applied. That's we make use of Ohm's law most times. However, there are more complicated circuits which cannot be simplified using Ohm's law. So for such circuits, we apply Kirchhoff's laws, or we say Kirchhoff's laws are applied. So what is Kirchhoff's laws all about? Now Kirchhoff has two laws. We have the first law, which is known as the current law, and we have the second law, which is known as the voltage law. All right. The first law, being the current law, is also known as the junction rule. And then the second law, being the voltage law, is also known as the loop rule. So we're going to take a look at the first law. Now here we have Kirchhoff's first law, also known as Kirchhoff's current law, KCL, or the junction rule. Now the rule states that the algebraic sum of current in a node or junction is 0. Mathematically, we have sum of I equals 0. Okay, that's the sum of current in a node or a junction is always 0. Now it can also be stated as the algebraic sum of current entering a node equals sum of current leaving the node or junction. So what then is a node? A node is simply a junction, alright, where more than two paths intersect or meet each other. This is a node. For instance, we have this part, we have this part, and we have this part here. Okay, so in order to call something a node, it has to be a junction where more than two parts intersect or meet each other. We have the same thing here. This is a node. We have 1, 2, 3, 4, and 5. Okay, so this is a node. Now let's take a look at the law again. It says the sum of current entering a node equals sum of current leaving the node or junction. Now, if you look at this diagram, what are the currents entering the node? You can see here that we have the direction. Okay, we have currents I1, I2, I3, I4, and I5. So what's the direction here? We have I1 leaving the node, I2 entering the node, I3 leaving the node, alright, I4 entering the node, and then I5 also entering the node. So according to the law, we're going to say that I1 current entering equals current leaving. So we can write it this way: sum of current entering, alright, entering the node equals sum of current leaving the node. So what are the currents entering the node? I1 is leaving the node. We have here I2. I2 is entering the node, so we're going to have I2 plus, how about I3? I3 is also leaving the node. How about I4? I4 is entering the node, so we have plus I4 plus I5 is also entering the node. We say plus I5, and that will be equal to sum of current leaving the node. What are the currents leaving the node? We have I1 and I3, so we have I1 plus I3. All right, so this is Kirchhoff's current law. You can present it this way, or you can present it the other way, which says the algebraic sum, all right, of current in a node is equal to 0. If you want to present the whole of this in this method here, or in this way here, all we need to do is move this current, okay, to this other side of the equation, and we're going to have I2 plus I4 plus I5, okay, plus we move I1 to this side, we're going to have minus I1, okay, plus you move I3 to this side, you have minus I3, and this is equal to 0. So this is what the current law is all about. If we want to look at an example here, we can select I1. We can take I1 to be 2 amps. I2, let's take it to be 1 amps. I3, let's take it to be maybe 0.2 amps. I4 to be maybe 0.8 amps. Alright, so let's use this example here to solve the unknown current I5. So we're going to have I1 plus I2. Sorry, sum of current entering equals sum of current leaving. So we're going to have I2 plus I4 plus I5. Remember, I5 here is the unknown. So we have 1 amps plus I4 being 0.8. We have 1 plus 0.8, and then plus I5, which is unknown, that's what we're looking for here, equals I1 and I3. So we have 2 plus 0.2. Okay, so let's use this to calculate I5. Remember the current rule. Sum of current entering equals sum of current leaving. And we have a junction here. That's why we want to apply the current rule. We have more than two paths coming to a point. Okay. So I5 here, we have I1 plus 1 plus 0.8. That will give us 1.8 plus I5 equals 2 plus 0.2. That will give you 2.2. So I5 will be equal to, we'll move 1.8 to this side of the equation. We have 2.2 minus 1.8, and that's going to give us 0.2 minus 1.8. That will give us 0.4 amps. 0.4 amps. Alright? So if we fall back to the rule again, sum of current entering equals sum of current leaving. The current entering are just I1 plus I3, right? I1 and I3. If we sum the two of them, we're going to have 2.2. Now the current leaving, we have I2, I4, I5, all right? If we should add them up, let's see what's going to give us. We have 1 plus 0.8 plus 0.4. Okay, that's also 2.2. Okay, so you see here that Kirchhoff's current law has been applied. Sum of current entering equals sum of current leaving. Now let's see if the algebraic sum of all these currents will give us 0. That's the algebraic sum of all these currents in this node will give us 0. So we have I2, I4, I5. Alright. Now remember, initially it was I2 plus I4 plus I5 equals I1 plus I3. Now, how did we convert this to a negative sign? We moved it to the other side of the equation and it became minus. Another way of doing this, you can do it this way. Because all the currents are not in the same direction, they are not going to have the same sign. So we can say let the currents entering be positive and let the currents leaving be negative. That's applying it this way. Sum of currents in a junction or node equals 0. So now looking at I1, I1 is leaving, so we can take it to be negative. Alright. I2 is entering, we take it as a positive current. I3 is leaving, you take it as a negative current. Okay. And then I4 is entering, we take it as a positive current. I5 is also entering the node, we'll take it as a positive current. Okay, so if we want to apply it this way, sum of currents in a node or junction equals 0. Some of the currents will be positive, some of them will be negative. The ones entering the node, you take them to be positive. The ones leaving, you take them to be negative. So applying it now, let's see if our answer here, I5 equals 0.4, is in line with Kirchhoff's current law. Now we have I2. I2, we have it to be 1 amp. So we have 1 plus I4, we have it to be 0.8 plus I5, we have it to be 0.4. Then plus I1. I1 is a negative current. Why? Because it's leaving. So we have plus minus, all right, plus minus is minus, so we have minus 2, and then we have plus minus, we have minus i3 is a 0.2, and that will give us 0. Okay, so you see that our answer here, I5 being 0.4 amps, is in line with Kirchhoff's current law. Now, we can also look at Kirchhoff's current law in this diagram. Okay, this is a diagram that looks like a typical question under DC circuit analysis. Okay, now in this diagram, discover that we have three currents. Whenever you see a question like this, first you try to identify the currents. We have current I1, we have I2, and then we have I3. Now we can call this point a node or junction. Why is it a node or junction? We have more than two paths meeting at this point. Okay, we have 1, we have 2, and we have 3. So this is a node. We cannot come here and say this is a node, okay, or maybe here is a node. No. In order to call something a node, you need to have more than two paths. Okay, it's like a junction. You need to have more than two paths meeting at that point. So you can call it a node or junction at that point. So applying Kirchhoff's current law here, remember we said sum of currents entering the node equals sum of current leaving. What are the currents entering? We have I1 and I2. So in this case, we can simply say I1 plus I2 equals current leaving, which is I3. Alright, so Kirchhoff's laws, current law has been applied here. Now let's take a look at the voltage law. Now Kirchhoff's voltage law, which is the second law, alright, it is also known as the loop rule. Okay, the loop rule. I'm going to explain what a loop is all about. Alright, Kirchhoff's voltage law, that's the second law, is also known as the loop rule. And then the first law, which is the current law, is also known as the junction rule. Alright, junction rule. Now, the loop rule, which is the voltage law, Kirchhoff's voltage law, KVL, states that the algebraic sum of all the voltages around any closed path or loop must be equal to 0. Algebraic sum of all the voltages around any closed path or loop must be equal to 0. What's a loop? Or what's a loop? Is simply a closed path. Okay, so this is a loop. In this diagram here, or for this question, we have two loops. You can see it here, loop 1 and then loop 2. Okay, so this is one closed path and this is another one. If we had extended this diagram a bit, let's say we have something like this now added to this, then we'll have loop 1, loop 2, and loop 3, because this is now another closed path. Alright, so a loop is simply a closed path. Alright, this is a loop, this is another loop. So in this question, or in this diagram here, we have two loops. Now, according to the voltage law, the sum of all the voltages in a loop or closed path is equal to 0. Sum of all the voltages in a loop or closed path is equal to 0. So we'll go around the closed path, alright, and we add all the voltages in that closed path. We add all the voltages in that closed path, and then we equate it to 0. That's what it means. Alright, so now where are the points where you have voltages? That's very, very important. Okay, now the first point where, let's take loop 1 for instance, on this loop here. The first point where we have a voltage is this point where we have the cell or battery, the symbol of cell or battery. The voltage here is A1. Okay, so there's a voltage here. Alright, looking at loop 2, we also have a voltage here. Anywhere you see a cell or battery, they'll write the voltage next to it or close to it. So we have a voltage here, we have another voltage here. Now, another point where you always see a voltage, or you must also consider a voltage, is across a resistor. All the points where you have resistor in your circuit, there's also a voltage. They may not state it for you, but you need to know that. All right. So here we have a voltage across this resistor R1. There will be a voltage. Now to calculate the value of that voltage, that's where we'll now make reference to Ohm's law, which is V equals IR. So for R1 now, the voltage across this resistor will be V1. You can label it as V1 equals I1 times R1. That's the voltage across this. All right. And then if we want to look at the voltage across this second resistor, you can label it as V2 equals I2 times R2. And then the voltage across this third resistor, we can take it to be V3 equals I3 times R3. All right. Don't forget the points where you see voltage. Okay. Where you're going to see voltage is where you have a cell or battery. Okay, there's always a voltage here, and this one is very easy. They'll just write the voltage very close to it or next to it. You just see something like 2 volts, and then you know there's voltage here. The other one, which most times is not very clear, is across a resistor. Do not forget, anywhere you see resistor, there must be voltage there or there is voltage there. And how do you calculate the voltage? You use Ohm's law. We have the resistor, you're going to be given the resistance there, and then you're going to be having current flowing across that resistor. So to calculate the voltage, we make reference to this law, Ohm's law. For this one, we say V1 equals I1 R1. For this one, you use the current passing through the resistor times the resistance. For here, you say the current passing through this resistor times the resistance of the resistor. All right, so that's it. So if we want to look at this loop now let's separate them, the different loops. We have loop 1. So let's look at loop 1. Let's apply Kirchhoff's voltage law for loop 1. According to the law, sum of all the voltages in this loop must be equal to 0. So we have E1, can take this to be our first voltage, E1 plus the next point where we're going to have a voltage is across this resistor 1. All right. So how do we get the voltage for across this resistor 1 here? We simply apply Ohm's law, like I said earlier, I1 times R1. So say plus, you write I1 R1. All right. You go to the next one here. Talking about loop 1, remember, we want to get the voltages, sum of all the voltages in this loop, and then we equate it to 0. All right, so we have E1, we have the next one. Now across this one, now what's going to be the voltage? We have plus the voltage across this resistor. How do we calculate it? Ohm's law again, I3 times R3. So we have I3 R3. Then we say equal to 0. Sum of all the voltages in a loop or closed path will be equal to 0. So this is the loop. This is a loop. This is a closed path. This voltage, this voltage, this voltage here equal to 0. So that is Kirchhoff's voltage law. Kirchhoff's voltage law. All right, for loop 1. Now we can also apply the voltage law for loop 2. All right, so this is loop 2. Let's see how we can apply the voltage law. We have loop 2. All right, now what are the voltages? Okay, you can see most times, okay, I'll come to this direction, but sometimes it can give you the direction on how you should move around the loop. Okay, here they gave us a direction. Look at this other one too. They gave us the direction how we should move. So we're working with this. All right, though you can decide to move in this other part, you can also decide to move in this other part here. All right, but whatever direction you're using, you have to be consistent with it. So let's continue with this. Loop 2. This is loop 2. It's a closed path. It's a closed path. So what's the voltage here? What's the sum of the voltage here? We have E2 to be our first voltage here. So we say E2 plus the next voltage here. All right, how do you calculate it? I2 times R2. Remember, wherever there's a resistor, there'll be a voltage. So we have plus I2 R2. Then plus the next voltage here, that will give you I3 R3, right, equals 0. All right. So we have voltage here, we have voltage here, we have voltage here in this loop. So there's no other voltage here. All right. So that will be equal to 0. Now, the voltages can either be positive or negative. They can either be positive or negative. Just like we had the current to be positive and negative, I said take current entering the node to be positive, take the ones leaving to be negative. We can also have a voltage that is positive and the voltage that is negative. And that's where we now make reference to the sign convention for the voltage. All right. So how do we now know the voltage that is positive and the voltage that is negative? All right. So let's start with the first one, across a resistor. Remember, across every resistor, we must consider a voltage, or must include a voltage there. So across a resistor, how do we know when we have a positive voltage and when we have a negative voltage? Now, it depends on the first thing, the direction of current, and then the direction transversed around the loop. All right, that's the direction in which you're moving around the loop. That's what we mean by direction transverse around the loop. Okay, so across a resistor, to know whether a voltage is positive or negative, we need to consider the direction of current and then the direction transverse around the loop. Taking this as an example here, we have current moving in this direction, direction transverse around the loop in this direction. All right. Now, before we come to this, you need to understand something, that whenever current flows in a circuit, it flows from a region of higher potential to a region of lower potential. Current flows in this direction. Okay, I'll take that again. Whenever current flows across a resistor, okay, very important. Whenever current flows across a resistor in a circuit, current flows from a region of higher potential to a region of lower potential. Whenever current flows across a resistor in a circuit, it flows from a region of higher potential to a region of lower potential. So this is a resistor. We have current flowing in this direction. So obviously this current will flow across this resistor. All right. So the current will be flowing from a region of higher potential to a region of lower potential. Now the region of higher potential, we use a positive sign to represent it. Region of lower potential, we use a negative sign. So we are from region of higher potential to a region of lower potential because the current is flowing in this direction. Okay, the current flows from a region of higher potential to a region of lower potential. So if your current is in this direction, before the resistor here, you're going to have high potential, and then after this point, you're going to have low potential. Whereas if the current was flowing in this other direction here, okay, we're going to have moves from a region of higher potential to a region of lower potential. So here will be higher, that's positive, and then here will now be negative. So the direction of the flow of current is very, very important. All right. So now, how do we know if this is going to be a negative voltage? Remember, we have a current here, and then this is a resistor. Okay. So if we want to calculate the voltage across the resistor, we say Ohm's law, V equals IR. So we have IR here. So now this voltage, now is it going to be a positive voltage or a negative voltage? First, you must put your signs. All right. Current flows from region of higher potential to region of lower potential. We've considered the direction of the flow of current. Now, the second thing being the direction transverse around the loop. That's how you're moving around the loop. We are moving around the loop. For instance, we're moving around the loop in this direction. All right. So it simply means you are moving from negative to positive. All right. Basically, that means a voltage rise. Okay. Since you're traversing around the loop in this direction, you're moving from low potential to high potential, and that's a voltage rise. Anytime you're moving from negative to positive, is voltage rise. If you're moving from positive to negative, okay, it's voltage drop. We're talking about the direction transverse around the loop now. All right. First, we use the direction of the current to get our sign conversion positive to negative. Now, to know whether this voltage is positive or negative, we now consider the direction transverse around the loop. We are moving around the loop in this direction. So we are moving from negative to positive, that's low potential to high potential. So this is a voltage Alright, so this is a positive voltage. Alright, so there's no point putting a negative sign here. Now coming to this other example, remember, to know whether a voltage is positive or is going to be negative, first you must consider the direction of the flow of current and then the direction transversed around the loop. So looking at what we have here now, direction of the flow of current, current is flowing in this direction. Now do not forget, and you must always remember, that current flows from a region of high potential to a region of low potential across a resistor. So this is our resistor here. Current is flowing in this direction. So we're going to have our region of high potential to a region of low potential. The current is flowing in this direction. Alright, so across the resistor, if the current is flowing in this direction, we are going to have before the resistor high potential, after the resistor low potential. If it were to flow in this other direction across the resistor, before the resistor high potential, after the resistor low potential. So this is the direction of the flow of current. Now the next thing will be the direction transverse around the loop in order to tell us whether this potential difference will be negative, this voltage or potential difference will be negative or positive. Alright, don't forget to calculate the voltage here. We need to apply Ohm's law. V equals IR. We have current, and then this resistor will have a resistance. Let's label it as R. So the potential difference or the voltage across this resistor will be I times R. So we have IR. Alright, this is the voltage across this resistor. So how do we now know whether it's going to be positive or negative? We need to consider the direction transverse around the loop. Okay, now look at the direction transverse around the loop here. We are moving from positive to negative. Remember, first you use your current to put your signs, your sign conversion. You have positive high potential to low potential based on the direction of flow of the current. Now direction transverse around the loop. If we are moving around the loop in this direction, you discover that we are moving from high potential to low potential. All right, that's from positive to negative based on the flow of current, the direction of flow of current. All right, so you discover that as you're traversing around the loop, you're moving from high potential to low potential, from positive to negative. And since you're moving from high to low, this is going to be a voltage drop. All right, voltage drop. So the potential difference or the voltage there is going to be negative. Okay, so the direction transverse is what will enable us to know whether the voltage is going to be a positive voltage or a negative voltage. So this is what we have here. All right, please, this sign conversion is very, very important as long as Kirchhoff's laws is all about, is concerned. So now let's look at applying the law, all right, in a loop or in this loop here. If we want to apply the law here, remember, let's just consider the points where we have resistor. So we have a resistor here, R1, we have R2, we have R3. All right, so now first, the direction of the flow of current across the resistor. Don't forget, current flows from a region of high potential to a region of low potential across a resistor. Now current is flowing in this direction in this case, so we'll label this part here before the resistor as high potential, after the resistor as low potential. Okay, for this other one again, the current is flowing in this direction. Okay, so don't forget, current flows from a region of high potential to a region of low potential across a resistor. So we have high potential, low potential. It's flowing this way. And then for this resistor, resistor 3, current flows from a region of high potential to a region of low potential across a resistor. So we have before the resistor high potential, after the resistor low potential. Now let's find out the voltage or the potential difference that will be negative, and then the one that will be positive. Now we need to consider the direction transversed around the loop. Okay, so we are transversing around the loop in this direction. So first we get to E1, and then when we get to this other one here, you're transversing around the loop in this direction. So you discover that you're moving from high potential to low potential. Okay, when you're transversing around the loop. So since you're moving from high potential to low potential, this is a voltage drop. All right, a voltage drop. So we call it a negative voltage. So you put a minus sign here. So when solving or applying the loop rule, you must consider this. All right, you must put your negative sign here, else your answer is going to be wrong. And then you're still transversing around the loop. You get to this third resistor. You're moving from a region of high potential to low potential. Okay, so this is also going to be a voltage drop, negative voltage. That is for loop 1. All right, now going to loop 2, we're transversing in this direction. All right, so you discover that you're moving from region of high potential to low potential. Okay, so this is also a voltage drop. You get to the third resistor, you're moving from high potential to low potential. So this is also a voltage drop. So this is how we know our negative voltage and our positive voltage. Okay. If let's say we were transversing around the loop in this other direction, all right, that's in the opposite direction here. You discover that as you're moving in this direction, this is going to give you a voltage rise. Okay, you're moving from negative to positive, low potential to high potential. So this will now be positive I3 if we were moving in this direction. And then this one will also be what? Positive I2 RO2. Okay, it doesn't change anything, just that you need to be consistent with your direction. All right, now the next point, if you recall, I said earlier that there are two main points where you see voltage in a loop or closed path, where you have a cell or battery and then where you have a resistor. So I've considered the one for resistor. Now let's consider the one for cell or battery. How to know our signs. Now every cell or every battery will always have a positive terminal and a negative terminal. So we have the positive terminal, we have the negative terminal. Positive terminal and negative terminal. Okay, so how do we now know the direction? How do we now know the one that's going to be positive and the one that will be negative? It's very easy also. For this one, since you have a positive terminal and a negative terminal, you're going to consider the direction transverse around the loop. If you're transversing from positive to negative, you take it as a negative um, potential difference or voltage. So we have minus there. If you're transversing from negative to positive, you take it as a positive potential difference. So looking at what we have here, we have E1, we have loop 1 moving in this direction. Discover that at E1, we're moving from negative terminal to positive terminal. From negative terminal to positive terminal. So take this as a positive voltage. So we'll leave it this way. Alright, so that's the only cell or battery we have for this part here. If you come to E2, discover that you're moving in this direction. You're moving from negative terminal to positive terminal. So you take it as a positive voltage. Alright, so basically this is just all about Kirchhoff's second law. This is what Kirchhoff's second law is all about. Alright, you can take the video, you can pause the video and try to understand it better. You can also take it backwards, watch it again and try to understand all these points, the sign convention and all of that. It is very, very important, as long as application of Kirchhoff's laws is important. You can watch this part again and try to understand it better. If there's any question, you can always drop it in the comment section and I will drop a reply for you. So the next thing we are going to talk about is an easy step-by-step guide on how to approach questions involving DC circuit analysis. That is applying Kirchhoff's laws, basically. All right. So now, number one, or the first thing here is to identify the currents and how they flow. You must identify the currents in that circuit and how they flow. Number two is to apply the current rule or the junction rule. Apply the current rule or the junction rule. And then number three is to take into consideration the sign convention for the voltages. Don't forget to talk about the sign convention for voltages, where the voltage is positive and where the voltage is negative. And then number 4, we talk about applying KVL, Kirchhoff's voltage law, also known as the loop rule. All right, taking potential difference around each loop. All right, take potential difference around each loop. Now, this question here, we have a question here. They said, find the currents I1, I2, and I3 in the circuit shown below. Find the current I1, I2, and I3 in the circuit shown below. So let's apply this method to solve this problem. Okay, let's apply this step-by-step guide to solve this problem. Okay, now going by the step-by-step guide, it says first identify the currents and how they flow. What are the currents we have here? We have current I1, current I2, and then current I3. Identify them and how they flow. You see that I1 is flowing in this direction, I2 is flowing in this direction, I3 is flowing in this direction. And then number 2, they say apply the current rule or the junction rule. Apply the current rule or the junction rule. Okay, so what's the current rule? Sum of current entering the node equals sum of current leaving the node. So where is our node there? This is not a node because this we have just these two connecting. A node, don't forget, we said, is a point where more than two parts meet. So this is a point. And then we have 1, 2, and 3. Okay, meeting at this point where more than two parts intersect or meet. So we have 1, 2, and 3. So this is our node. Okay, so applying the current rule, we say current entering equals current leaving. So what's the current entering here? We have I1 entering this node, I3 also entering the node, and then I2 is leaving. So come down here, we'll simply say I1 plus I3 equals I2. All right. Current rule or junction rule. Sum of current entering equals sum of current leaving. Sum of current entering equals sum of current leaving. Current entering we have I1 and I3. Current leaving we have just I2. So this is current rule. So we can label this as equation 1. Now number 3, we need to take into consideration the sign convention for the voltages. And how do we do that? All right. Before we know the voltage that is positive and the one that is negative, we need to consider the direction of flow of current across resistor. All right. And then our positive and negative terminals for the cell or the battery. All right. So now looking at what we have here, this is a resistor. Okay, where are the points we are going to have voltages in the first place? Okay, before we talk about the sign convention for the voltages, we need to first identify where we have voltages. This is a resistor, there will be a voltage here. This is a battery, there will be a voltage here. You can see it is already stated 8 volts. All right, this is a resistor, there will be a voltage here. Okay, this is a battery, you can see it's stated there already 12 volts, and here we have 6 volts. So these are the points where we're going to have voltages. So let's impute our signs for this diagram. So don't forget, current flows from a region of high potential to a region of low potential across a resistor. This is a resistor. We have current flowing in this direction. All right. So across the resistor, we're going to have from high to low based on the direction of flow of current. So label the part for high potential as positive, the part for low potential as negative. From a region of high potential to a region of low potential. Now for this other one, this 16 ohm resistor, we have current flowing in this direction. Current will always flow from a region of high potential to a region of low potential. So the part before the resistor, positive, the part after the resistor, negative, based on the direction of flow of current. Current flows from a region of high potential to a region of low potential across a resistor. So we have high to low. Now the next thing will be our battery. This is negative terminal, this is positive terminal. The longer one is always the positive terminal, and the smaller one is the negative terminal. And this is positive terminal, negative terminal, negative terminal, positive terminal. All right, so that's it. So now we've taken into consideration the sign convention. All right, now let's apply the voltage rule. All right, we take potential difference around a loop or closed path. So we can take this as our loop 1. Let's move in this direction. We'll take this as our loop 2. Okay, so we can move around the circuit in this direction. Let's move around the circuit in this direction. The same thing here. Let's move around the circuit in this direction. Okay, so now for loop 1, let's take this as loop 1. It's a closed path, so we can call it loop 1. So from here we have a voltage of 6 volts. All right, so we're going to say 6. We're taking sum of all the voltages round. We're going to say 6. Okay, now this 6, is it going to be positive or negative? Discover that you're moving like this around the circuit, okay, in a clockwise direction. All right, so this 6 is going to be a negative voltage or positive voltage. As you're moving around or you're transversing around the loop, you discover that you're moving from negative to positive. All right, so you can say from low potential to high. So this is a positive voltage. Okay, so leave it as 6. They'll say plus, what's the next voltage we have here? All right, the next voltage we have here is the voltage across a resistor. And then remember, to calculate the voltage, we use Ohm's law. All right, so going by Ohm's law, we are going to have the current times the resistance of this resistor. All right, that will give us the voltage across this resistor. So we're going to have I1 times R1. Our R1 is 10 here, which is the resistance of this guy. Okay, so say 10 times I1, and that will give us 10 I1. All right, so we have 10 I1. All right, now this 10 I1, which is the voltage across this resistor. Remember, how did we get 10 I1? We multiply the current by the resistance. We used V equals IR. V equals IR. That's how to get the voltage across resistor. Now this 10 I1, is it going to be a negative voltage or positive voltage? Discover that you're moving in this direction. All right, so as you're moving, you're transversing around the circuit or this loop. Discover that you're moving from high potential to low potential, high potential to low potential. All right, so this is going to be a voltage drop based on how you are transversing around the loop. We have a voltage drop, so this will be minus. Okay, then we have plus. You go to the next one, you're transversing around the loop in this direction. You're moving from high potential to low potential for this voltage here. From high potential to low potential, high potential to low potential. All right, as you're moving around. Okay, so this is now going to be a negative voltage from positive to negative. Okay, so you have minus 8. Okay, apply the voltage law, take potential difference around each loop. So by the time we add everything based on the voltage law, sum of all the voltage, are we is that all for the voltages? Yes, that's all. We have 6, 10, and this. There's no other voltage again. All right, so based on the voltage law, sum of all the voltages is equal to 0. So we have this plus this equals 0. That is our voltage law. So simplifying this, we're going to have 6 plus minus is minus. We have minus 10 I1 plus minus is minus, so we have minus 8 equals 0. All right, so now simplifying this, let's take like terms. We have 6 minus 8. All right, 6 and minus 8, that will give us minus 2 minus 10 I1 equals 0. All right, if we're trying to get I1, let's move minus 2 to this other side since we're trying to get I1. All right, so we're going to have minus 10 I1 equals 2. So in that case, we divide both sides by minus 10. We're going to have minus 10 I1 over minus 10, okay, over minus 10 equals 2 all over minus 10. And this is going to cancel out this. You're going to have I1 equals 2 divided by minus 10. We have, I think that should be 0 minus 0.2, so we have minus 0.2 amps. Okay, that's for our I1. Now, if we want to get I2, if we want to get I2, or the other current, so this is for loop 1. Loop 1 has given us I1 to be minus 0.2 amps. Okay, sum of all the voltages in loop 1, we have first current. Now let's see if we can get any other current. Now, going by what we have, let's take sum of all the currents or voltages, okay, in this loop, which is loop 2. Okay, so for this one, we start from this voltage here, which is 12 volts. From here, we'll move around in this direction. Okay, so here we have the voltage here to be 12. So we have 12. This is loop 2. Okay, and this was loop 1. So we have loop 2. From moving in this direction, we have positive to negative. So we can say this is a voltage drop. All right, so we have minus 12 rather than just writing 12. 12 is the voltage on this battery here. Okay, minus 12. You move towards this other one, you move from negative terminal to positive terminal, low potential to high potential. Okay, so this is a voltage rise. So we have plus 8. Okay, we are moving around, and then we get to this other one here across this resistor. Okay, across this resistor, you discover that you're moving from positive to negative. Okay, here is positive, we move from negative to positive, so we just leave it as 8 volts, positive 8. Now, by the time you move around, I get to this resistor, you're moving from positive now to negative. So this is a voltage drop. A voltage drop. First, what's the voltage here? Voltage here is going to be the current across this resistor times the resistance. So we have I2 times 16, and this is 16 I2. All right, that will be the voltage here. All right, now this 16 I2, is it going to be positive or negative? Since we're moving from positive to negative, across this resistor is going to be negative. So here we're going to have plus, all right, minus 16 I2. If we simplify this, we're going to have minus 12 plus 8, plus minus is minus 16 I2. Don't forget, this will be equal to 0. Sum of all the voltages, all right, according to Kirchhoff's voltage law, equals 0. So this is also equal to 0. This plus this plus this is all, that's all the voltage we have for this loop, equal to 0. Now simplifying it further, we're going to have minus 12 plus 8, minus 12 plus 8, and that will give us minus 4. So we have minus 4 minus 16 I2 equals 0. Now let's try to get I2. We'll move minus 4 to this other side of the equation. We're going to have minus 16 I2 equals 4. To get I2, divide both sides by minus 16. We have minus 16 I2 all over minus 16 equals 4 all over minus 16. And this will cancel this, and then you're going to have I2 to be equal to 4 divided by minus 16. 4 divided by minus 16, and that will give us minus 0.25, minus 0.25 amps. Okay, so now let's get, we've gotten our I1, we've gotten I2. So what's left now is I3. So how do we get I3, of calculate the value of I3? We just make reference to our equation 1 here. Equation 1 says I1 plus I3 equals I2. To get I3, we'll make reference to this equation. So we'll just say substitute I1 and I2, okay, in equation 1. Substitute I1 and I2 in equation 1. All right, so what is I1? I1 is minus 0.2 amps. So rather than writing I1, we write minus 0.2, all right, plus I3. What's I3? That's what we're looking for. So we have plus I3, all right, and then equals I2. All right, equals I2. What's I2 again? Minus 0.25 amps. Minus 0.25. All right, so to get I3, we'll make a subset of the formula. Move minus 0.2 to this other side of the equation, and you're going to have I3 equals minus 0.25, okay, minus 0.25 plus 0.2. So we have minus 0.25 plus 0.2, and that should give us minus 0.05. So I3 is equal to minus 0.05 amps. All right, so here we now have our value for I1, I2, and then finally I3. So we've answered this question, all right, for Kirchhoff's law. So we have minus 0.2, minus 0.25, and then minus 0.05 amps. Okay, so that's our answer. Now the reason why we have a negative current is because the flow of current, okay, is supposed to be in the opposite direction. Okay, so that's why we have negative currents here. But this is our answer here: 0.2 amps, 0.25, and 0.05. You can also attempt this question and decide to move around your circuit in this direction. Remember I said the direction transverse in the circuit does not really matter. In this case, I transverse around the circuit in this direction, both loops in a clockwise direction. You can attempt your own, transverse both of them in anti-clockwise direction, or you can take this one in clockwise and then this one in anti-clockwise. It really does not matter. You're going to have the same answer. So you can try it out and then drop your answer as a comment, all right, as a comment at the end of this video. All right, if you get a different answer, also indicate and I'll look into that.